Hey y'all, we are Memphis Kim University and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And today we're going to be continuing our advanced derivative topics and we're going to be talking about particle motion. So particle motion is the biggest real-world application of calculus. So it is one of the biggest topics on the AP exam, especially the AB portion. Keep in mind that we already introduced particle motion a little bit when we were talking about basic derivative topics in a video I believe called Derivative Miscellaneous Topics or something like that, where we learn we have three main functions: position, velocity, and acceleration. And what you do is you take derivatives as you want to go down. So for example, velocity is the derivative of position, acceleration is the derivative of velocity, acceleration is the second derivative of position. So today what we're going to do is we're going to really jump into particle motion and we're going to talk a lot about all the rules that come with particle motion. So particle motion comes with its own set of vocabulary words, and what we're going to do is we're going to have rules for them and apply those rules. So unlike usual, I'm not going to talk a huge intro on how to do every single question. We're going to try to tackle the questions as they come. But again, in particle motion, it's position. That's where you are on the number line. So whenever you're thinking about this, think about a nice little number line. We have a little dot particle just traveling along, having the time of his life, and he just travels along this line. It's only 1D, one dimension. He cannot travel up or down. The particle can only go right or left or along the line, one direction or the other direction. So that's going to be our particle. There's going to be position. We're going to take the derivative often, and we're going to use velocity. And then finally, we're going to take potentially another derivative to use acceleration. So let me give you a brief sort of outline of which 5 questions that I want to cover in this video. We are going to cover quite a bit, so let's get started. One thing before we get started though that I want to mention is that there are going to be eventually integrals in particle motion, but because this is an advanced derivative topics video, we're only going to keep it on the derivative side, so we're not going to apply the fundamental theorem of calculus. Be on the lookout for that later on in your course. We do have several videos on the fundamental theorem of calculus where a big component of that is particle motion. But let's start particle motion in this context. So we're doing particle motion. Where in particle motion, the big thing is position, velocity, and acceleration. Again, to go from one to the other, you take derivatives, of course. And then what questions are we going to be talking about in this video? We're going to be talking about particle at rest. When is the particle at rest? When does the particle move forward, backwards? So forwards, backwards, and it changes direction. So these are sort of movement questions of the particle. The second question we're going to talk about quite extensively is going to be total distance. This one I find a little bit annoying, especially when you don't have the power of integrals, but we're still going to learn the process, and we're going to see that while the process is a little bit tedious, it's not the worst thing in the world. We can still do it. The third thing we're going to talk about is speeding up, slowing down. So whether at a certain time or over a time interval, is our particle going faster or is our particle slowing down, going slower? So then the fourth thing we're going to do, we actually probably already mentioned before because I like this question too much, which is finding the absolute maximum minimum of a certain particle motion function, either position, which is farthest right or farthest left, velocity, or acceleration. So we're going to be using the closed interval method that we learned when we learned shape of curves. The 3-step process. So it's going to be add maximum min of S, V, or A, one of them, of course. And then 5, the last one we're going to do is we're going to consider whether two particles are moving closer to each other or away from each other at a certain time. So particles moving closer or away at a certain time. And again, each of these questions just has a rule or a process. Once you know the rule or process, the actual steps aren't that hard to sort of carry out. The main step is take a derivative, potentially draw a sign chart, things like that. Keeping in mind that, of course, we have S, V, and A. So in each of them, they might rely on just one of the functions. They might rely on position, velocity, acceleration, or a combination. And that's really how the rules, what you need to know in order to answer these questions about these rules. But if you want, you can pause the video right now, write these down. I'm going to quickly erase them so that we can just get started, because again, this video might be kind of long because there's so many questions that we want to talk about. But each one does have a rule. This is the order of the questions that we're going to do them in. And then finally, for each one, hopefully I'll be able to explain it as it comes. So let's get started. So the first one is the easiest one by far probably. It's particle at rest, moving forward, moving backward, or changing direction. So let me give you an example of that. So let's erase this. So particle moving forward or backwards. Let's say we have a particle and its velocity. So just be wary of which function is given. If the given function is position, if the given function is velocity, if the given function is acceleration, you're going to be carrying your steps quite differently because each rule depends on a certain function. So in this case, we're going to start off with velocity. It's going to be t minus 1 squared times t minus 3. And we're going to have time be greater than 0. So this is often a given in particle motion questions because t is time, of course, and we only want time to be positive or 0. We don't want time to be negative. So again, if you don't know particle motion, the general gist is you have this particle traveling along the curve. The position is where the particle is on that curve. So I like to think about it as mile markers, like mile marker number 5 or mile marker number -7, something like that. Its velocity, which is the derivative of position, is how fast the particle is traveling along the curve. So it's something like the speedometer in your car. Keeping in mind, though, it can be negative, and negative means it will be going backwards, as we'll see. So velocity has a direction and a magnitude. Finally, acceleration is how fast the particle is moving. How fast is its speed going up? And for example, if you step on the accelerator, your velocity is going to be getting higher and higher and higher. So those are the three main functions. In this case, what we want to answer is when is the particle at rest? When is the particle moving forward? Because again, direction matters with velocities. When is the particle moving backwards? The opposite. And finally, when does the particle change direction? So by the time we get to this fourth question, we probably will know the answer. And of course, you might not be asked all four of these questions, but you're going to see that once you have a sign chart of velocity, you're going to be able to answer all these four questions very, very quickly. So that's why sometimes they're asking combinations. No matter what, the first step is to draw a sign chart of velocity, so let's do that. Be wary that if you need to watch our sign chart video, certainly do that. But it looks like in this case, we're going to have 3 zeros from 2 different factors. Looks like this factor right here contributes 2 zeros itself because the multiplicity is 2. And then this one contributes 1 0. So it looks like if I can do math in my head, we have 3 zeros in total. So we're going to plot this 1 and 3. And because we have something 3, that means we have a polynomial that's cubic. Everything is positive. So remember that odd positive functions start at the bottom, end up at the top. So it's going to go starting at the bottom, ending up at top. Then when you consider zero behavior, notice that it'll bounce at 1 because this power is even. And it'll go through the number line at 3 because this power is inherently just 1. So it's going to bounce here and then go through. If I can sort of make my tick mark really big so that it'll go through at the point. So keep in mind though that we do have time greater than 0. This sort of sign chart goes on forever, of course, but we're going to cut it off at 0 because again, we don't want negative velocities. So negative times, not negative velocities. We do want negative velocities because in this case, notice that it'll be negative velocity here, positive velocity here. So now that you have the sign chart of velocity, and potentially later in the course, or maybe already right now, you could be finding this graph using a calculator. No matter what, if you have a picture of velocity, you should be able to answer these 4 questions pretty quickly. So again, each of these questions have justification, sort of like shape of curves. F is increasing when F prime is positive, and then you answer the question. This is sort of the same idea. It's going to be a question, particle at rest. It has a justification that you just need to know. And in this case, particle at rest, logically speaking, it's just when velocity is 0, you're parked in your car. So this is just velocity 0. So you just look at the sign chart and see where the velocity is 0. Looks like it's 1 and 3. So it's going to be t is equal to 1 and t is equal to 3. So again, question, justification, answer. Particle moving forward, well, that's when your velocity is positive. So you're going this way. So that's when velocity is positive. Looks like in this guy right here, it's going to be from 3 to infinity, or times greater than 3. Then particle moving backwards, well, that's when the reverse, that's when velocity is negative. Looks like we have two intervals here, from 0 to 1, 1 to 3. Be sure to not include 1 because at 1 the velocity is at rest, so it can't be moving backwards. So it's going to be from 0 to 1, and then 1 to 3. Finally, when does the particle change in direction? Well, that's when velocity changes signs. Either velocity goes from positive to negative because it's moving forward and then moving backward, or velocity goes from negative to positive. It's moving backwards and then forwards. So this is the rule is particle velocity changes signs. So it looks like in this case it's only t equals 3 because notice it goes from negative to positive. 1 does not count because it's negative and then negative. So it's t is equal to 3. So those are the four main questions that are asked sort of at the beginning of particle motion free response questions, or very simple multiple choice questions. They're again pretty easy because they only rely on the sign chart of velocity. Keep in mind though that if we were given position at the very beginning of this video, we would have to take the derivative just to find velocity. But in this case, we wanted to start off with something simple, so velocity was the given one. But again, just know your rules really well, particle moving forward, velocity positive, and things like that. So for now, what we're going to do is we're going to erase this, and we're going to proceed for another question. So let me erase this. So now we're going to do some of the harder questions. So the first question I want to do is total distance. So find the total distance that a particle travels. So particle traveling. Anytime you're doing total distance, there has to be a time period given. So in this case, we're going to do over first 3 seconds. And then finally, we do need a position formula. So it's going to be S of t is equal to, I believe we want t cubed plus 6t squared minus 15t minus 2. So this is going to be our position formula. So when you start learning integrals, you're going to learn a lot easier formula for total distance. That's going to be the integral of the absolute value of velocity. But in this case, because we don't know that, what we need to do is we need to do a very tedious method. But once you know how to do the steps of the tedious method, the hardest part is going to be plugging in numbers. So it's not the hardest process in the world. So let me describe the steps for you. First off, what we're going to do is we are going to find velocity, because that's usually the first thing we do in every single question, by taking a derivative. Then we're going to draw the sign chart of velocity. So draw a sign chart of velocity just like we did in the previous one. But first we have to find it. Keep in mind that we're going to add this interval on top of the sign chart of velocity because we don't care about the entire velocity's sign chart. We only care about our given interval. Finally, we're going to apply this formula for every single chunk or subinterval of the sign chart of velocity. For every subinterval. Every consecutive subinterval. So what you're going to see is the sign chart is going to be something like 1 to 2, 2 to 7. So we would apply it for the interval 1 to 2 and also 2 to 7. Let's not put minuses here. Let's put stars just to make sure that you know that this formula is just absolute value. So these are going to be steps. So if you know a little bit of physics, then you'll know the difference between total displacement and total distance. Total displacement is finding the distance, or sorry, let's start over. Total displacement is the difference between where you started up and where you ended up. Theoretically, you can travel a lot, but if you end up in the same spot, your total displacement isn't going to be very big. Total distance is exactly what it sounds like. It's how much you travel, no matter if you're going left or right. So if I start right here and I just move back and forth, back and forth, back and forth, the total displacement won't be very big, but the total distance will be pretty big because I'm traveling back and forth, and I want to count all of this traveling. So that's why we do this formula. What it does is it defines the total displacement for all the positive velocity pieces and also all the negative velocity pieces, and we're counting that all as positive total distance. You don't really need to understand exactly why it all works. Hopefully that explanation was adequate. You do just need to know these steps for this process. So let's get started with this process. So the first thing what we're going to do is we're going to first find velocity. So in this case, we're going to do the power rule again, 3t squared plus 12t minus 15. We're going to factor this derivative. So it's going to be 3 times, looks like I can take it a 3, plus 4 minus 5. Finally, I'm going to factor this polynomial right here. So it's going to be 3 times t minus 1, I believe, and then t plus 5. So it looks like my two values are t is equal to negative 5 and t is equal to 1. So now what we're going to do is we're going to draw a sign chart. This sign chart is pretty basic. It's just a parabola. It only has two factors, crossing at negative 5 and 1. Positive, negative, positive. The signs actually don't matter that much. Basically, we just have to do this for every single subinterval on this sign chart. We do want to add the endpoints to the sign chart, keeping in mind that first 3 seconds, remember, it implies that it's from t equals 0 to 3. Those are the first 3 seconds because you start off at time equals 0, you end the stopwatch at t equals 3. So we're going to add that to the sign chart. So 0 is about right here, 3 is about right here. So again, we only care about the interval from 0 to 3. So while we drew this nice pretty sign chart, we're not going to look at anything past 0 or anything past 3. We're only going to look at the sign chart within 0 to 3. So it looks like in this case, all we had, there are two intervals. We have the interval from 0 to 1, and then we have the interval from 1 to 3. So again, what you do is you apply this formula for this interval, and then you apply this interval for this interval. And you do it as many times as many small chunks of interval that you have. So for example, if it was 0, 1, 2, 3, you would do 1 to 0, 2 to 1, 3 to 2. So in this case, we're just going to do 2 of them. So it's going to be for the first interval. How do we denote this? Let's say from 0 to 1. 0 to 1. And then we have a second interval from 1 to 3. And again, this is the most annoying part of the process. What you do for each of these intervals, so this guy right here, and then this guy right here, you're going to apply this formula. So what we're going to do, we're not going to plug into velocity. We're going to take both of these numbers and plug it into position and subtract, and then take the absolute value. So let's do that here. So this is going to be s of 1 minus s of 0, and we're going to try to find this. So s of 1 shouldn't be too bad because we're plugging in 1. So it's going to be 1 to any power is 1, so it's going to be 1 plus 6 is 7. 7 minus 2, I believe, is 5, and then 5 minus 15 is negative 10. So in this case, s of 1 is negative 10. 0 is a lot easier. When you plug in 0, everything goes away except this minus 2. So it's just going to be minus 2 at the end. Keep in mind that when you take the absolute value, some students mess this up because they'll add up all the differences of s of b minus s of a, the difference in the positions, and then they'll take the absolute value at the very end. But that's incorrect. What you do is you take the absolute value of each individual piece. So in this case, we're going to take the absolute value of this. Negative 10 minus 2 is negative 12. The absolute value of negative 12 is 12. So again, just take the absolute value of each individual piece and then add up the answer at the end. So finally, we do have to do the same sort of process, s of b minus s of a with absolute values from 1 to 3, because that's going to be where the velocity is positive. So we want that displacement as well to add to our total distance. This was negative displacement, but we're considering it to be positive. And now we're going to add the second piece. So we're going to do this formula again, s of 3 minus s of 1. So let's see if we can do this. Well, if you plug in 3, maybe we can do the work a little bit on the side. You're going to get 27 because 3 to cube. Then you are going to get 3 times 3 is 9, I believe. 9 times 6 is 54. Then you're going to subtract off 45 because 3 times 15 is 45. So this is just math. And then we're going to subtract off 2. So if I can do math correctly, 54 minus 45 is 9. 9 plus 27 is 36. 36 minus 2 is 34. So if I can erase all my work here, looks like s of 3 is 34. Again, I think this is the most annoying thing because you have to do these values, but you just calculate them. Finally, it is minus, and then we already found s of 1, it's negative 10, but just keep in mind that the formula is s of b minus s of a. So if s of a is negative, that just means it's a negative position, meaning it's to the left of the origin. You're just going to write minus negative 10. So be careful with these negatives. It's minus minus. So in this case, it's going to be 44. So finally, at the very end, you add these two numbers together. Looks like we're going to get 56 as our total answer. So this is the second question, total distance. It is quite annoying if you have paper and pencil and are given position. So again, what are the steps? What you do is you find velocity, you draw a sign chart of velocity, then you add the interval that you're dealing with onto the sign chart of velocity to cut it off. And in this case, we have two consecutive subintervals, one from 0 to 1 and one from 1 to 3, based off the sign chart of velocity and the interval that you care about. And then what you do for all of those subintervals, 0 to 1, 1 to 3, so thankfully we only had two of them, what you do is you apply this formula, the absolute value of S of B minus S of A, where S is the position. So that's what we did. We were careful, we did absolute values for every single piece, we added the answer in the end, and then we were good to go. So that's total distance, quite a difficult question. Let's move on and do another particle motion question that's pretty common, speeding up, slowing down. So a lot of these are just knowing which functions to use. In this case, you use position and velocity. So the next question is speeding up, slowing down. So particle speeding up, slowing down. This also involves quite a lengthy process, but hopefully you'll see what I mean. So particle is moving, speeding up, slowing down. Keep in mind that particles speeding up, another way to say this is particles speed is increasing, and then particle slowing down is particle speed decreasing. So there's a really known fact about speeding up and slowing down. I'm not going to explain it too much, but a particle is speeding up when its velocity and acceleration have the same sign, and a particle is slowing down when the velocity and acceleration have different signs. Obviously, if your velocity is like 100 and you're accelerating and accelerated, then your velocity is getting bigger and bigger and bigger, 100, 200, 300. Same thing though if you're going the negative direction. If your velocity is negative 100, that means you're just going 100 backwards. And if your acceleration is negative 10 or something like that, then your velocity is going to become negative 110, negative 120, negative 130. So in magnitude, your velocity is getting bigger and bigger and bigger. So, or in magnitude, of course, and the magnitude of velocity or the absolute value of velocity is speed. So that's the rule we're going to focus on. Again, a lot of my students just memorize it. A particle is speeding up. We can already write the rule down here. A particle is speeding up when V and A have same signs. So velocity and acceleration have same signs. And then a particle is slowing down when velocity and acceleration have different signs. Speeding up, slowing down. So V and A have different signs. So before we talk about this, let's talk about it in sort of a general context on how that asked it. Sometimes they ask it over an interval, and that's what we're going to do here. We're going to try to answer over the entire number line, find every single time where the particle is speeding up or slowing down. Keep in mind though that sometimes it's only at a specific point, and when it's at a specific time, all you do is you plug in that time into your velocity formula or into your acceleration formula, and you're good to go. Just compare the signs. Velocity and acceleration have the same signs, it's speeding up. Particle velocity and acceleration have different signs, then it'll be slowing down. So that's that. And as you can tell by the rule, potentially, looks like we're going to need V and A for these questions, and also we're going to need to know sign charts because we need to do same signs and different signs. So first off, we need a function. So in this case, my function is going to be S minus t cubed over 3. Again, this is just going to be a given, plus 3t squared minus 8t plus 3. So this is going to be my position, and again, what we need to do is we need to find two derivatives automatically. So what's going to be our first derivative? Well, all we're going to do is the power rule. Keep in mind though that when we do the power rule for this first guy right here, we certainly don't want to do the quotient rule. All we're going to do is we're going to take the 3 and drop it to the front. The 3 and the 3 will cancel, so you're just going to be left with minus t squared. Then we have 6t because of this power rule, and then finally we have minus 8. So now we're going to finish factoring this. Looks like I can take it a negative, so it's going to be negative t squared minus 6t plus 8. So that's pretty easy to factor. It's going to be t minus 2 times t minus 4. So it's going to be negative t minus 2, t minus 4. So then what we need to do is we need to find acceleration now. So to find acceleration, well, again, what you do is you take the derivative of just velocity. What's the derivative of velocity? That derivative is a little bit easier. It's going to be minus 2t plus 6. And that's basically it. So now once we have your two derivatives, because particle is speeding up when velocity and acceleration have the same signs, and because particle is slowing down when velocity and acceleration have different signs, what we need to do is we need to draw the sign chart of velocity, and we need to draw the sign chart of acceleration. And again, I'm going to draw them over each other. I feel like it's not as good to draw one single sign chart with both functions, because if the sign chart gets pretty cluttered, what I'm going to do is I'm going to draw one sign chart on top of each other. So in this case, we're going to first draw the sign chart of velocity. Pretty simple thing, because it's t minus 2 times t minus 4. Keep in mind that because this is negative, we're dealing with a negative parabola, so it's going to cross through at 2, and then it's going to cross through at 4, and then it's going to look like this, and then it's going to be negative, positive, and negative. Before we continue, we should note that, like normal, we're t greater than or equal to 0, because we want to have no negative times. So we're going to cut it off at 0. Then what you do is you draw acceleration. So hopefully we can stick a little sign chart of acceleration here on the bottom. But the acceleration of the sign chart of acceleration is even easier than the sign chart of velocity. What it is it goes through the point 3, because negative 2 times 3 is 6. Negative 6 plus 6 is 0. So that's the x-intercept of this line. And keep in mind that lines only are positive slope lines or negative slope lines. Because this is mx plus b, the m is negative 2. That means our slope is going to be negative. So we're going to have this sign chart right here, positive and negative. So now we're ready to do the question. And again, the rule is particles speeding up when velocity and acceleration have the same signs. Particles are slowing down when velocity and acceleration have the different signs. So when you look at this right here, what I do is I take the smallest number I see on both sign charts, and then I arrive at the next smallest number that I see on both sign charts. So let's see this in action. So notice that the smallest number in both sign charts is 0. That's a very logical place to start. And then the next number, this next smallest number I see is 2. So from 0 to 2, what we're going to do is we're going to compare the sign charts of velocity and acceleration, because a particle speeds up when the velocity and acceleration have the same signs, both positive or both negative, and a particle is slowing down when velocity and acceleration have different signs. So from 0 to 2, notice that velocity is negative. While 2 is not on the sign chart of acceleration, we can sort of picture where it goes. From 0 to 2, around right here, notice acceleration is positive. So on this sign chart, from 0 to 2, velocity is negative, acceleration is positive. They have different signs, and if they have different signs, that means the particle is slowing down. So the particle is going to be slowing down from 0 to 2. Because velocity is negative, acceleration is positive. Finally, as we continue this process, we're going to take our number 2, because we ended up at 2, and we're going to go to the next smallest number we see on either sign chart. So it looks like that number will be 3. And notice between 2 and 3, while 3 is not on the sign chart, you can still picture it. 2 to 3, the velocity is going to be positive. Same thing with the acceleration from 2 to 3, the acceleration is going to be positive as well. So that means that the particle is going to be speeding up, because the velocity and acceleration share the same signs. So we're going to have from 2 to 3 is part of the answer for speeding up. So we can write the word on maybe to add some English. So now let's keep going. So the number we ended up with on our last interval, the last endpoint, the right endpoint is 3. So what we're going to do is we're going to hit the next number we see. The next number we see is the final number. It's 4. And notice from 3 to 4, 3 is about right here. 3 to 4 on the velocity sign chart is positive. 3 to 4 on the acceleration sign chart is negative. So we have different sign situation. That means the particle will be slowing down. So it's going to be 3 to 4. Finally, we're going to consider one more interval. The very last interval is going to be 4 all the way towards infinity, 4 to infinity. Notice that from 4 to infinity, 4 is about right here on the sign chart. Both sign charts are negative. That means that the particle will be speeding up, because velocity and acceleration have same signs. So 4 to infinity is the final answer. So this is speeding up, slowing down. The basic process is first find velocity, then find acceleration, draw the sign chart accurately for both of them on top of each other, and then compare signs for each little interval that you might potentially encounter. So 0 to 2, 2 to 3, 3 to 4, 4 to infinity in this case. And the rule is particle speeding up when velocity and acceleration have the same signs, particle slowing down when velocity and acceleration have different signs. So again, quite a lengthy process, just like total distance, but once you know the process, it's still just taking derivatives, still just drawing sign charts, and then applying a rule. So let's do a process that we might be more familiar with, absolute max or min of particle motion questions. So let me erase this. So what we're going to do is we're going to find the abs max, I believe, of this we're going to have a position formula of s of t, and it's going to be, let's see if I can see it on my computer screen there. It's going to be t cubed minus 9t squared plus 8t minus 2. And what we're going to do is we're going to try to find the absolute max and min, not of position, but of velocity of this particle from t is equal to 2, t equals 1, let's say, that's an easier number, to t equals 4. So this is going to be your standard absolute max or min process using the closed interval method. We're going to locate the function, we're going to take the derivative, find some zeros, and then we're going to form a beautiful little table, and that's going to be our goal. Keep in mind though that sometimes you're finding the absolute max or min of 3 different functions. Sometimes it's position, sometimes it's velocity, sometimes it's acceleration. No matter what, you do the same process. You do need to locate the function. That's very important. What am I taking the absolute max or min of? So in this case, notice it won't match the given. I'm finding the absolute max and min of velocity, but the given is position. So just be wary of that. Also, keep in mind that they might not use the words absolute max or minimum, especially with position. Usually they use the words farthest right or farthest left. So just keep in mind that farthest right means the absolute max of position. So you'd be doing the closed interval process on position itself. Same thing with farthest left. Farthest left means absolute minimum of position, your leftmost position. So what you're going to be doing is you're going to be doing the closed interval method on position. But for now, because this question is on velocity, we're going to do the closed interval method on velocity. So let's get started. So again, I like to do it in 3 steps. Locate. So the locate is always taking the locate is always finding the thing or taking the max of. Sometimes you take a derivative, sometimes you don't take a derivative. So in this case, because we're finding the velocity, the absolute max or min velocity, we have to find velocity itself. So in this case, the velocity will not match the given. We have to take the derivative just to find it. So in this, we're going to use the power rule. Power rule being 3t squared minus 18t plus 8. So that's the derivative there. And this is the function that we're going to care about for the rest of the question. We no longer need the given at all because we want to focus on velocity because we're finding the absolute max or min velocity. That's why I like to highly encourage my students to write the locate step even if it did match the given, because that's the function you care about the most. When we start constructing the table, we're going to be plugging in into the locate and not, for example, the given position. The given position is only there to help us find the function we care about, but once we have the function we care about, sort of like how we deal with people, we're going to abandon the people we don't need anymore. So we're going to abandon the position function that we don't need. So then we're ready to go for the process. We have step 1, locate. We're going to focus on this guy right here, and we're going to do the process on this locate. So the step 2, of course, is the critical point step. So it's taking the derivative and setting it equal to 0. If you want, you can of course know that v prime of t is equal to a of t, but it doesn't really matter in this case. All you're doing is you're taking the derivative of the thing you're taking the max of. In this case, it's v prime. It happens to be a. I'm not going to write a because it doesn't really add to the question. So it's going to be 6t minus 18. We're going to set it equal to 0. So just get in the practice of just writing the derivative equals 0, potentially on a free response question. If you write derivative equals 0, you get more credit than just writing the derivative. But in this case, the derivative equaling 0 means that t is equal to 3, because 3 times 6 minus 18 is 0. So now we're ready for the table part, my favorite part of the question, or maybe my least favorite part, I haven't decided yet. So remember that when you form this table, what you need is you always need at least 2 points. Those are going to be your endpoints. So it's going to be 1 and 4. Then you include any critical points from step 2 that fit within those critical points. So in this case, because we have t equals 3, 3 does go between 1 and 4, so we are going to include it in the table. But for example, if we had gotten 3 and 8, well, we wouldn't have included 8 because 8 is not between 1 and 4, and we only care about the times between 1 and 4. Finally, the hardest part and the most tedious part is to find the right side of this column. Keeping in mind that, again, we do not care about this position formula at all. We only care about the locate. So when I plug in these numbers, I'm certainly not going to plug it into position. I'm going to plug it into velocity. So it's going to be v of t. So when we plug in 1, some of these numbers might get a little bit awful, but I believe in us, we should be fine. When we plug in 1, it's going to be 3 minus 18 plus 8. It's going to be 11 minus 18, that's negative 7. Then when we plug in 3, that looks kind of bad. 3 times 3 times 3 minus 18 times 3. So plus 8, of course. Let's try to do this. Well, it's going to be 27 minus, this is the least important part of the question, obviously, but 18 times 3, I believe, is 54 plus 8. This is negative 27 plus 8, which is going to be, I don't even know, negative 19. Finally, we do have to plug in 4, unfortunately. It's going to be 3 times 16 because 4 squared is 16. Again, this is not very important. Just know where to plug it in. That's a lot more important. Negative 18 times 4 plus 8. So 3 times 16, 16, 32, 54 as well, I think. No, that's not true. 16, 32, 48. And then 18, 36, 72 plus 8. I can't do this math. 48 plus 8, what is that? 56. 56 minus 72, I believe that's negative 16. So that's going to be negative 16. So it looks like all of our velocities are negative, but that's fine. Let's go for the answer. So in this question, what's the absolute max? That's the biggest number. That's going to be negative 7. So abs max velocity is negative 7 at t is equal to 1. The abs min velocity is negative 19 at t is equal to 3. And that finishes the question. So hopefully you recognize that this process is the absolute maximum min process that we have come to love, of course. 3 steps: locate, taking the derivative, setting it to equal to 0, and forming a table where you plug in the left values of the table into your locate step. The only thing that people mess up probably is that they want to answer their own questions. So they see this nice function of position and they immediately try to find the max or min of position. So they'll write the position right here, they'll take the derivative, and they'll try to draw the table. But that's not correct. What you need to be very, very aware of is what are you taking the absolute max or min of. In this case, velocity. So my very first step is find velocity, and I don't need the position anymore for the rest of the question. So it's just the process. The important thing is what function are you doing the process on? Once you know the process, we do this process so often that people can usually get it, as long as they can get that first step. And writing this locate step, in my opinion, will help you out. But this is how you do absolute max or min. Let's do one more question, moving closer or away from each other. So let's erase this. And let's do one last question. So my last question is, I'm going to have 2 particles. I'm going to have particle A. I'm going to have particle B. So these are 2 good friends, 2 little particles, and they're just moving along a curve. They're moving along the same line. So they're going to have 2 velocities, or 2 positions. So let's label this S of B of t and S of A of t. So this first function is going to be the position of particle A. The second function is going to be the particle B's position. Particle A, I think I need t cubed minus 3t squared plus 2t plus 5 is going to be my particle A's position. And then particle B, I want to be t squared plus 4t plus 2. So these are my 2 particles. And what I want to know is that at t is equal to 1, is the particle moving towards, are the 2 particles moving towards each other or away from each other? Are they getting closer or farther? So we have these 2 particles at t equals 1. Are they going like this? Are they going like this? Theoretically, they could be going neither, actually. They could be going like this or this. But our 2 particles are either going to be going closer or away from each other, as you'll see. So this is the last one that involves a method. We can talk about the method. What you need is you need to find S and V of both particles at t is equal to 1, because it relies on where they are and what direction they're going to. So for example, if this is particle A and this is particle B, if they're positioned like this and they're going in this direction, then they're going to be moving closer to each other. But if they're in the reverse, if they're already past each other and they're moving in the same direction, notice that they'll still be going farther away from each other, even if they're traveling in the same direction. So you really need to know both things, position and velocity for both of these particles. So what we're going to do is we're going to draw a nice little number line, where on this number line, the positions will be on the number line. So positions will be on the number line. Velocities won't be on the number line because you can't really see speeds when you look at a car, but we're going to know what direction it's going based off the velocities. So positions will be on the number line, velocities will tell me direction. Bringing it back to the very beginning of the video, if a particle has a positive velocity, it's going forward. If a particle has a negative velocity, it's going backwards. So let's find the position and the velocity for both of these particles. So I'm going to take first particle 1, or particle A. So what we're going to do is we're going to plug in our number. It's a nice convenient number 1, and we're going to try to find where is particle A at time is equal to 1. So when you plug in 1 here, it looks like it's going to be 1 minus 3 plus 2. All of those will cancel out. So it's going to be left with 5. Then we're going to find the velocity of the particle. So we do need to take a quick derivative. It's going to be 3t squared minus 6t plus 2. And then what we're going to do is we're going to plug in 1. So when you plug in 1, it's going to be 3 minus 6. That's negative 3 plus 2 is negative 1. Keep in mind that the only thing we care about this number is that it's negative. Because if it's negative, again, that means the particle will be moving backwards. So that's all we care about. If it was negative 12, the answer would be the same, as you'll see. So now what we have to do is we have to do the same thing for particle B. We need to find the position and the velocity. So this is V of A at 1. So for particle B, we're going to plug in 1 into this guy. 1 plus 4 is 5, I believe. 5 plus 2 is 7. Then we're going to find the velocity. One last derivative for this video. 2t plus 4, because the derivative of 2, of course, is 0. So then when you plug in 1, you're going to get a velocity of 6, which is greater than 0. Again, you don't actually care about the number itself, just its sign, positive or negative. So now we're ready to answer the question. So I'm going to draw a quick little number line here at the bottom of the board, and then I'm going to first place the particles' positions on the number line. So just think about this number line again as a road, basically, where the mile marker is the position of the particle. So at mile marker 5, you would be able to find A. So this is mile marker 5. And at mile marker 7, you would be able to find B. So mile marker 7 is B. Then we're going to draw an arrow indicating what direction each of these particles are going. So because the velocity is negative for this particle, that means that particle A will be moving towards the left. So it's going left. And because particle B is positive, that means the velocity is going this way. Because the velocity is positive, that means the particle is moving towards the right. So notice that in this case, because of our beautiful picture and because of the position and velocities that we found, these two particles are going to be moving away from each other. They don't like each other anymore. They're going to go like this. Keep in mind though that it is still very, very important to find both position and velocity. What some students think is that you only need to base off velocity. Like if the velocities don't have the same signs, then the particles are moving away from each other, but that's not the case. Notice that if we switch the positions of A and A was still going left and B was still going right, and these particles were switched, then they would actually be moving closer to each other. So sort of like with speeding up, slowing down, where you don't just need velocity, you need velocity and acceleration. For moving closer or away from each other, closer or farther from each other, what you need both position and velocity. But that really concludes our video. Hopefully you sort of have a great overview on particle motion. We did talk about several questions, and particle motion is tricky because it has so many rules that are applied to it. But once you know the rules and once you know how to apply the rules, and the rules mainly involve taking derivatives, maybe drawing sign charts, plugging in things. The processes themselves, while a little bit annoying, aren't the hardest things to carry out. So it's still derivatives, it's not integrals, not the hardest part about calculus. We did talk about several rules. We talked about particle moving forward and backward, particle at rest, particle change direction. Then we talked about total distance, where we found velocity and did the formula of the absolute value of S of B minus S of A. Then we talked about speeding up, slowing down. A particle is speeding up when velocity and acceleration have same signs. A particle is slowing down when velocity and acceleration have different signs. The fourth question we talked about was absolute maximum min of a particle motion function. We did the three-step process, the closed interval method, on the appropriate function. Locate the function, find the critical points, and then by taking the derivative, setting it equal to 0, and drawing the table, where we plug in those values into our locate. Finally, we did moving closer or away from each other, and this one relies on position and velocity. You draw it on a number line. Velocity is not on this number line, but it tells you the direction. And if they're going away from each other, they're going away from each other. But again, it's based on both position and velocity. So as you can imagine, this is a lot of information given to you in just one video. So if you need more practice with this, I highly encourage you to watch our Girls Teach Calculus video. I'm going to link that in the description below, where one of my former students practices all these questions and more for particle motion. So she practices moving closer away from each other. She practices speeding up, slowing down, total distance, and things like that. It's definitely a great video to watch if you want more practice with particle motion. Keep in mind though, we haven't even finished our particle motion coverage, because remember that this is just the derivative side. So when we start talking about integral topics in our playlist integration topics, for example, when we start talking about fundamental theorem of calculus, finally we'll be moving from not just S, V to A, but we'll be going backwards, A, V, and S, using integrals. And when we talk about average, we'll talk about how there's two formulas for average velocity, 1 over V minus A, the integral of velocity, and also the algebra slope of position. So particle motion will pop up here and there, so hopefully you'll continue along with us as we explore every single calculus topic on the AP exam, so that eventually you're going to be able to know all the particle motion questions imaginable. Particle motion is also one of the main AB free response questions. It is not a BC free response question, but it is a main AB free response question. So we did create 11 free response questions just devoted to particle motion, where we go from difficulty 1 through difficulty 10 after an overview video. So if you want to practice actual, or not actual, but questions similar to particle motion free response questions, no matter what the difficulty is, the easiest ones to the hardest ones, be sure to check out that playlist. But no matter what happens, thanks for joining us for this quite difficult video. I hope to see you next time, even if no matter what video you end up choosing to watch. Thanks again for your support, and I hope to see you next time.